I welcome all students. This is Professor Vishal Maitre from Department of Electrical Engineering, Bharati Vidyapit, deemed to be University College of Engineering, Pune. So, in this particular lecture, we are going to study about the optimal power flow analysis that is under computer applications of power system. Now, let us go through the understanding of the session contents. Now, before going into session contents, what we are going to study as an objective for this particular session, that students will get to know after studying this session the basic difference between the load flow analysis and the optimal power flow analysis. What is the importance of this optimal power flow analysis from the analysis point of view in real time power system, and how it is going to be beneficial as compared to the normal load flow analysis that we have studied in AC/DC load flow analysis part. So let's quickly go into the session. So these are the session contents. I'll be starting with what is optimal power flow, what are the importance of objective functions that we are going to consider in optimal power flow, the definition of objective function, and the constraints that we are going to consider during the optimal power flow analysis, the methodologies that we are going to consider, and at the end, if you are having any doubt, you can just post your doubt so that I can get back to you for any queries that you are facing. So let us start with optimal power flow. Now, what is optimal power flow? So let me first quickly tell you the difference between the normal load flow analysis and the optimal power flow analysis. So the normal load flow analysis, what we consider the control variables that we are considering at any particular bus, because bus we are considering as a node for load flow analysis. So at that particular bus, the control variables, we are predetermining it or pre-specifying it. That means before performing the load flow analysis, now here I am limiting myself up to for AC load flow. In general, we are going to talk for AC load flow, that we are having these control variables which are predetermined. That means suppose the voltage which is continuously changing on real time basis because of the load and the generation changes throughout the power flow. This voltage magnitude, we are pre-specifying it to 1 per unit, and the angle is 0 for the slack bus, and all other buses, the angles we consider some value. So this function, this value is called the predetermined value. So this predetermined value is for the control variables. But in actual optimal power flow analysis, what we are going to do is all this optimal power flow, the control variables that we are going to have is at the best operating level with the constraints that we are going to impose on them to have the predefined objective which we are going to achieve for the optimal power flow analysis. So that is the basic difference. The other difference is that for normal load flow studies, we are considering only the steady state condition, which is the major drawback that is faced, because we cannot apply for the normal power system, because as you know, the power complexity of the power system is quite large, and it should have the analysis in real time data. So this is going to be the solution for that particular real time variables through this optimal power flow analysis, because it is going to help to get the real time data, whether it is in the complex form, and it is going to take very less computation time as compared to the normal load flow, because here we are considering the control variables with some constraints so that the system remains intact with the grid. That is, the system should be secure. The security of the system is the priority for us, so we have to maintain it. So let us quickly go to the definitions or the statement. What do you mean by optimal power flow? So it represents a problem determining the best operating levels for electrical power plants in order to meet the demands given throughout a transmission network, with the objective of minimizing operating cost. Now here two things to be highlighted, that the best operating levels, the levels that we are going to consider for the control variables that are going to maintain satisfying the demands. Whatever is the demand, we are going to satisfy it, and the main thing is the objective is minimizing operating cost. So this minimization of objective of minimizing cost is going to be very important for designing a economical power system. So OPF module, so I'm going to represent optimal power flow as OPF. OPF is going to be a model which is intelligent load flow. Now the normal load flow is the load flow, but we can call this OPF as an intelligent load flow because it employs the techniques to adjust the control setting through the governor action for the generator to adjust the generation accordingly to the satisfaction of the demand. Now here what we are going to do is we are going to obtain, or we are going to impose certain constraint on the operating conditions. Those constraints can be either equality or inequality constraints that we will be seeing it in the subsequent slides. So because of the active power flow is going to be non-linear, non-convergent, it has only the drawback that it requires more amount of calculations. But in actual time, as we know that entire distribution network is on the real time. So here real time, I'm specifying it that every 5 minutes we should have the data, how much is the active power or the total power flow analysis, so that it gives a clear idea of taking certain precautions to maintain the power system security, so that also the demand is accurately met. Now, what are the importance of objective function? Now, the prerequisite, one more thing I forgot to mention, the prerequisite that we are going to require is the mathematical point of view that is already covered in the 12th class, engineering basic mathematics, maths 1 or maths 2. So here what we are going to require is we are defining a function which has to be minimized or maximized, and the minimization or the maximization of the result is going to be imposed on that particular predefined function, which is going to be helpful for getting the optimum result. So your optimum results is means that we are getting the maximum value which is going to be beneficial, and minimum value which is going to bear more amount of cost. So here in optimum power flow, what we do is some of the control variables we are going to optimize, that is either to a minimum function or maximizing a function with a predefined objective. That predefined objective that we can say, yes, this function I have to minimize, or this other function I have to maximize, that I have to predefine. So the certain objective function which has to be minimized for the best operation of the power system is fuel cost, transmission losses, and reactive source allocation. These three important factors are for minimization. Note here we are focusing only on minimization because the maximization is the other point of view where we can go with ANN or some fuzzy logic network also. So usually the objective function is the minimization of total production cost of the generating units, because it is ultimately going to reflect it in the economic dispatch. We should have the minimum cost. That is why this scheduling and the minimization of the generating cost of the generating units is going to be treated as the highest priority as the operational requirement in power system, because we have to maintain it to optimum level. So the main objective, OPF also aims to optimize a certain objective subjected to network power flow equations, system and equipment operating limits. So it has to behave as a multiple tasking, or we can say at a multiple tasking objective. So one thing, it has to maintain the power flow. Second thing, it has to maintain the limits. Next thing, it has to maintain the constraints on that particular components that have been connected. So this condition is adjusting the available controls to minimize the objective function subjecting to its operating conditions as well as the security conditions or the requirements. Now let us see quickly the objective functions in OPF that can be defined. So I've divided it into two parts. One is active power objectives and the reactive power objectives, because when I say optimum power flow, here we are going to consider the active power flow and the reactive power flow. So the active power flow components that can be considered as objective functions for, so there are three main categories, whether we want for economic dispatch, environmental dispatch, or maximum power dispatch. So as we are saying, to have in terms of cost, we are going to consider mainly the economic dispatch in terms of minimum cost, minimum losses, maximum megawatt generation, that is the real power, active power generation, and the transmission losses should be minimum. Second is going to be the environmental dispatch, and the third is the maximum power transfer. And for reactive power objectives, it can be in the form of active and reactive power, that is MW and MVR respectively, loss minimization. So the goals, how these general goals are going to be set for reactive power: one is having minimum deviation from the target schedule. Whatever is the target, we have to achieve the target. There should be no deviation. The difference between the defined target and the actual should be 0. Minimum control shift to elevate violations. The controls, whatever is the governor controlling the generation part according to the power flow equations or the control variable constraints, there should be not much difference in the violation of the limits. Least absolute shift approximation of control shift, there should be minimum shift available for the control unit on the generator side. The next we are going to have is, now out of these out of these two major categories, active and reactive power objectives, what we are going to majorly focus is from the economical point of view, economic dispatch point of view, with equality and inequality constraints, with load and with unloading conditions. So for that we are going to require fuel or active power optimization, second is active power loss minimization, and the third is going to be the reactive power minimization to the cost of reactive power support. This is going to be very useful part. So let us see one by one. Here we are going to focus the objective function and the equations, problem or the solution for those equations for fuel cost minimization and the power losses minimization. As I have discussed that here we are going to focus in this lecture only on the minimization factors. So the next, total generation of the cost unit, it is going to be a function of generated power, which is going to be summation of I equal to 1 to number of generators that are connected in the system. So this is going to be a quadratic equation which is same like the regression. It is the part of the numerical methods for the quadratic equation, that is alpha I plus beta I into pgi plus gamma I pgi square. So this alpha, beta, gamma are the factors that are the multiplying factors that we are considering, and pj is going to be the main function for the quadratic equation. So as I have mentioned that we are going to define the objective function with certain constraints. So let us see the objective function. So the minimum power generation, generated power, the minimum generation cost of power generation, to be more specific here we are talking in terms of cost. So it is going to be the function of x and u vector. So that x and u vector are going to be the vectors that we will be discussing in subsequent slide. What is x, what are the contents that are in x vector and u vector that are going to be the controlling the factors. Now subject to satisfaction of equality and inequality constraints. Now here, as we know that we are considering the complex power flow equations, so all equations are going to be non-linear. So there we are going to study about the two constraints, equality constraints and the non-equality constraints. Please note that the equality constraints are going to be related only to the power flow equations, because we need to have a balanced power flow equations. There we cannot have the comparison with the power flow equations. And the inequality constraints are going to be the operational limits on the transmission lines or the reactive power flow. So the non-linear equality constraints is going to be g x comma u. So g we are defining the function for equality constraints. Similarly h we are defining the function for non-linear constraints, which can be either less than equal to 0, because we are opting for minimization. If suppose we are having an objective for maximizing the function, this inequality constraint would be h x of u, which is greater than equal to 0. So non-linear inequality constraints, we can see that u has to be between minimum and a maximum value. Similarly x should be between the minimum and maximum value. Let us see the next, the variables or the functions that have been defined, the meaning of those functions. So the function of pg is the total cost which is obtained from the function of x and u vectors, which is going to be a scalar objective. So g is representing the non-linear equality constraints that as I've mentioned we are going to consider only for power flow equations, and h x of u is the non-linear inequality constraints that we are going to consider the operational limits imposed on certain parameters or the control variables. So let us see what is there in vector x and u. As we can see that vector x contains the variables which can be either bus voltage magnitude, the reactive power output of the generators for the bus voltage, fixed parameters for the reference angles, non-control generators on for the reactive and active and reactive power, non-control active and reactive power on the loads, and fixed bus voltage for the line parameters. So out of these 6 categories you can select any one function or the two as the function which we are going to consider for the fuel cost minimization. In the next we can see the vector u, which includes the variable, as I've mentioned, certain limits on the operating conditions that we are going to consider for real and reactive power generation. that can be in the form of phase shifter angles, that is through the governor action. Net interchange means the interchange between the any two utilities, load megawatt and reactive power, that is the load shedding, which is going to be the power flow balance, or you can say the economic management, economic dispatching, so that the demand and generation are exactly matching with each other. It is not in actual, but the ideal condition is to obtain actual, but practically it is not achieved. DC transmission line flows, this we have covered in the previous lecture. Control voltage settings and load tap changing, transformer tap settings are important for controlling the minimization of the fuel cost that we are going to require. So these are the certain equality and inequality constraints that we are considering for fuel cost minimization. Please note that these constraints can be applicable for any other objective function also. So note that these equality and inequality constraints we can talk, it is going to be applicable for almost all the objective functions that we are defining in the optimum power flow problem. So the equality and inequality constraints are limits on all control variables, power flow equations, generator load balance, branch flow limits, that is how much is the active power and the apparent power flow flowing through each branch, bus voltage limits, active power, reactive power, reserve limits, which are in the reserve capacity which can be used in case of any failure in the generation units, generator reactive power limits, and the corridor transmission, which is between, where either it can be interstate, intrastate, or it can be at the international level. So these are very important. Now the equality constraints which are applicable for the load flow equations are the active and reactive power. You can see that it is depending as a function of voltage and del, minus PGI plus PDI. The summation of all this should be equal to 0. PD is going to be on the load side, PG is on the generator side. So where Pi is the function of V and del again, which is having the equation magnitude of Vi summation of I equal to 1 to n. Vj should be J, Yij, that is the bus admittance matrix, which is between bus I and J. Cos del I minus del J minus phi ij, that is the angle corresponding to these magnitudes of the voltage and bus admittance matrix. Similar equation is for reactive power, only difference is of the sign term. Yij is the bus admittance matrix with magnitude and its angle, and the load balance equation is going to be the generator minus load minus the losses. So these all should be equal to 0. So that is why we call this as equality constraints, because the difference, whatever is the power flow flowing through each component, the difference should be equal to 0 to match with the overall generation. So inequality constraints are the limits, as I mentioned it, through the line flow constraints. So it can be in the form of voltage. We can see there voltage should be between minimum and maximum value, that is the generated power generation, active power generation, reactive power generation, the difference between the voltage between the bus I and J, considering the node L, the angle between the node I and J, again the apparent power should be less than the maximum apparent power, the torque which is there, again the del, that is the power angle, should be between the minimum and maximum limit. Now the objective function for power loss minimization, the second part we are going to see here, it is going to be summation of all losses. So the power losses will be equal to K equal to 1 to L PLK. So these are the losses where we are going to consider individually in terms of voltage and phase angles, and that all we are going to combine it together. So I am defining it in the form of function GK VI GK, which is going to be function of the bus voltage magnitude and the angle corresponding to it, Vi square plus Vj square minus 2 Vi Vj cos del I minus del J. So it is again a form of the second order equation. So that function we can define in the form of objective function, because we have to achieve the target, or we can say that objective function as minimum losses. So it will be equal to summation of I equal to 1 to NL. Again the same equation GK Vi square plus Vj square minus 2 Vi Vj cos del I minus del J. So this is going to be a quadratic equation, and we are going to solve, we can solve this equation through any one of the methods that we will be discussing in next slide. So the constraints for this cost minimization will be same as the constraints for this power loss minimization will be same as cost minimization in terms of voltage and phase angle, and it should be noted that all these values are mentioned in rectangular form. So the objective constraints for objective function of power loss minimization is to have the generated active power, control voltage magnitude, reactive power injection, which is coming from reactive power, and the transformer tappings. So the objective is to minimize the power transmission loss function by optimizing the control variables within their limits. So therefore, no violations or any other quantities will occur in normal system operating conditions. So these are the main objectives. There we can have no violations occurring with certain limits. The equality and inequality constraints will be the same for the fuel cost minimization and power loss minimization as mentioned in previous slides. So what are the objectives and applications of objective power optimal power flow? So as we know that it can be solved on very large complex power optimization in real time in relatively less time. The calculations are going to be real time control, which is going to be beneficial from operational and planning point of view. It is also used in many modern EMS, that is energy management system. So the main goal is to meet the load demand which is required by the power system, maintaining the security of the system. The secondary goal of OPF is going to be maintaining the marginal cost that is going to be required for the power generation. So while economic dispatch, the control of this active power and the tap ratio, the phase shift angles, all these parameters are considered as the control variables to have the achieve the objective function that is defined. So the optimal power flow is able to monitor the issues including the overload or the low and high voltage problems. So you can call this as modernized techniques, which is going to be very beneficial to achieve the objective. So in case of any security problem is occurring, this OPI will modify its control so that the transmission, whatever is the transmission line is overloaded, that can be removed from the system to keep the system healthy and remain intact with the grid. So this is going to be very beneficial. So in the next lecture we are going to study about the optimal power flow solution methodologies, the gradient method, Newton-Raphson method, and the linear programming method. There are also intelligent methods or the advanced methods that we are going to study in next lecture. Thank you.